This is SpaceTime, Series 21, Episode 41. Coming up on SpaceTime, water vapor plumes discovered on Europa, why science's current knowledge of physics means EmDrives probably don't work, and the ultimate fate of our sun when it dies. All that and more coming up on SpaceTime. What appear to be plumes of water vapour have been discovered erupting into space from below the frozen surface of Jupiter's ice moon Europa. The findings, reported in the journal Nature Astronomy, provide tantalising new insights into whether the Jovian moon could support life. The discovery is based on a re-examination of data originally captured by NASA's Galileo spacecraft during its decade-long mission to Jupiter in the 1990s. The data was put through new, more advanced computer models in order to untangle a mystery, a brief localized bend in the magnetic field, which had gone unexplained until now. Previous ultraviolet images taken by NASA's Hubble Space Telescope in 2012 suggested the possible presence of water vapor geysers, but this new analysis used data collected much closer to the source and is considered strong corroborating support for the plumes. The study's lead author, Zhangji Zhai from the University of Michigan in Ann Arbor, says the data were there but needed sophisticated new modelling to make sense of the observations. At the time of the 1997 flyby, about 200 kilometres above Europa's surface, the Galileo team didn't suspect the spacecraft could be grazing a water plume erupting from deep beneath the frozen crust. But when they examined the information gathered during that flyby 21 years ago, sure enough, high-resolution magnetometer data showed something strange. The authors drew on what scientists had already learned from exploring water plumes erupting from the South Pole tiger stripes of Saturn's ice moon Enceladus. Material in those plumes became ionized, causing a characteristic blip in the magnetic field. And the same sort of blip was present in the earlier Europa data, but had never been explained until now. Galileo carried a powerful plasma wave spectrometer to measure plasma waves caused by charged particles and gases around Europa's atmosphere. Zhai's team pulled that data as well, and it also appears to match the theory of a plume. But the numbers alone weren't able to paint the whole picture. So the authors layered the magnetometry and plasma wave signatures into a new 3D model which simulate interactions of plasma with solar system bodies. The final ingredient was the data from Hubble, which suggested the dimensions of the potential plumes. The result that emerged with the simulated plume was a match for the magnetic field and plasma signatures pulled from the Galileo data. Zhai is also a co-investigator on two instruments that will travel aboard NASA's upcoming Europa Clipper mission. Slated to launch in June 2022, Europa Clipper will explore the ice moon's potential habitability. From its orbit of Jupiter, Europa Clipper will sail through the moon in rapid low-altitude flybys. If plumes are indeed spewing water vapour from Europa's subsurface oceans and lakes, Europa Clipper will be able to sample the frozen liquid and dust particles looking for the ingredients of life. NASA's Galileo spacecraft was launched back in October 1989 from the payload bay of the Space Shuttle Atlantis on mission STS-34. Named after the famed Italian astronomer Galileo Galilei, it consisted of an orbiter and an entry probe. Galileo achieved Jovian orbit insertion on December 7, 1995, after gravitational assist flybys of both Venus and the Earth. As well as launching an entry probe down deep into the Jovian cloud tops, directly measuring the planet's atmosphere, Galileo was also the first spacecraft to undertake a close flyby of an asteroid passing close to 951 Gaspra. It also discovered the first moon orbiting an asteroid when it spotted Dactyl orbiting the asteroid 243 Ida. And Galileo also had a front row seat for the historic impact of the comet Shoemaker-Levy 9 into Jupiter in 1994, witnessing the giant Earth-sized scars caused by the massive collision. The data Galileo collected supported the theory of a liquid ocean containing more water than all the Earth's oceans under the icy surface of Europa. And there were also indications of similar liquid saltwater layers under the surfaces of both Ganymede and Callisto. The spacecraft also discovered that Ganymede possesses a magnetic field, and it found evidence for tenuous atmospheres known as exospheres around Europa, Ganymede and Callisto. On September the 21st, 2003, after 14 years in space and 8 years exploring the Jovian system and its 4 Galilean moons, Io, Europa, Ganymede and Callisto, Galileo's mission was formally terminated by sending the probe on a suicidal death plunge into Jupiter's atmosphere at over 48 kilometers per second, thereby eliminating the possibility of contaminating the local moons with Earth bacteria. You're listening to SpaceTime. I'm Stuart Gary. An EmDrive, or more accurately, a radiofrequency resonant cavity thruster, is an experimental design for a propellant-free propulsion system, which, if it actually worked, would violate 2 basic laws of physics: the conservation of momentum and the conservation of energy. The conservation of momentum states that any interaction can't have a net force. A consequence of the conservation of momentum is Newton's third law, which states that every action has an equal and opposite reaction. The law of the conservation of energy states that the total energy of an isolated system remains constant, irrespective of whatever internal changes may take place, with energy disappearing in one form and reappearing in another. It's the first law of thermodynamics. Energy can be changed from one form to another, but it can't be created or destroyed. Hypothetically, an EmDrive would produce thrust from an electromagnetic field inside a cavity without ejecting any mass. Several prototypes of this design have been developed and tested, the best known being by NASA's EagleWorks laboratories. And while some scientists have claimed to achieve a small amount of thrust from their prototypes, these achievements have never been replicated through the usual peer review processes, and that's raised concerns that these apparent observations may really be simply due to noise or some measurement errors. Hypothetically, an EmDrive would work on the same principle as conventional plasma thrusters or ion drives. But instead of ionizing something like xenon gas and shooting it out one end as thrust, virtual quantum particle pairs, which are constantly popping into and out of existence, would be ionized by microwaves generated by the drive, creating an extremely low-density plasma. Of course, the first problem is that virtual particles don't behave like plasma. And the second is that if they did, it still wouldn't be the same as the Casimir effect, as they still wouldn't have anything to push against, so couldn't be used for propulsion. Now, it's been suggested that time-varying electromagnetic energy densities could produce a local gradient in the gravitational potential, creating a sort of warp field in space-time. The problem there is warp fields have never been observed except in the Star Trek universe. However, they could potentially be tested using interferometry. In 2013, scientists used a warp field interferometer to try and detect warp fields over short distances in a symmetric resonant cavity. And that test apparently observed small anomalous effects. However, once again, the results were never replicated, and so it could simply have been interference from the heating of the surrounding air. To find out more about EmDrives, Andrew Dunkley is speaking with Dr. Fred Watson from the Australian Astronomical Observatory.
Is there any work developing this kind of technology?
There is work going on it, absolutely. If the drive that we're talking about is something that's sometimes called a radio frequency resonant cavity thruster, then there is work going on it. But it is so controversial that, as far as I know, no big-time players in this game are investing in it. But you can bet your life that DARPA will be looking at it. And DARPA is the Defense Agency's research wing in the United States. They do all kinds of really interesting research, which we sometimes hear about and sometimes don't. Basically, the idea is that you've got something that looks like a tin can, a conical. Well, all right, imagine a bucket, a metal bucket with no top and no bottom. And you set up an electromagnetic oscillation inside it. And the proponents of this drive say that actually generates a thrust. You pour microwaves into it and you get an unbalanced force coming out of the two open ends. So you get a large force coming out the big end and a small force coming out the small end. And those two forces add together. One's negative because it's in the other direction to the first one. And you get a net thrust that lets you push an object forward. So there has been quite a lot of work that's been described on this, but all of which seems to be pretty inconclusive. There has been some work done by NASA. There's a team which is known as the Advanced Propulsion Physics Laboratory, sometimes called EagleWorks, which doesn't really make an acronym, but never mind, which is the idea is that they look after exotic concepts for propelling spacecraft. And they've tested all kinds of things that you might describe as fringe proposals, and I think this is one of them. I don't know to what extent their work has been successful. They have published papers, but given that nobody has yet leapt on this and said this is the way of the future, I suspect that there are still doubts about whether it actually works. Part of the reason is it's very difficult to test. You've got to test it under experimental conditions, which means probably in weightlessness and in a vacuum. So it does mean you need to take one of these things up in space and actually try it out. I think there are plans for the Chinese government to test one of these things on its space station. But I think if you took a gang of 100 scientists and said, okay, who backs the EmDrive, it would not be that many. And more scientists would be looking at the ion propulsion drive, which is another, what was once thought to be exotic, where you've got an inert gas like xenon or something like that, and you feed it through, you basically turn it into a plasma and accelerate it out of a jet nozzle. So you're using solar power, the electricity generated by sunlight, to turn this gas into a plasma and blast it out the back of your rocket, but you're not burning anything. Now that's a conventional rocket in a sense, because it's taking something and firing it out the back, and the change in momentum is what lets you move forward. It's very different from the so-called EmDrive, which seems to be something that does not require an exchange of momentum. And that's why so many physicists struggle with it, because it seems to defy the laws of physics, and we don't really understand that, if indeed it does work. So I think there is work going on this. I think it'll be work that perhaps within the next year or two will come up with a conclusive answer as to whether this is a real potential solution to spacecraft design. But then you've got to find a way of generating the huge amounts of power that you need to make it work, because that is one of these things that does not come for free. You've got to get power into it.
And then you've got to control it. And if it's capable of the sorts of things that we're hearing about, then control is another factor that needs to be solved. And it also prompts a question in my mind, something we've talked about before, but not for a long time, of the same ilk as the scramjet. That's got a bit quiet, hasn't it?
The supersonic combustion ramjet, as it's called, scramjet. Look, there is work going on. I know that University of Queensland is still very active in this field, and I think there are, aerodynamicists at the University of Sydney who are also working on it. So once again, it's something that's work in progress. Clearly, rocket motors turn out in the end to be rocket science. It's pretty hard to do it right and to get things that will work, especially these exotic, what you might call fringe designs, like the EmDrive.
That's Dr. Fred Watson from the Australian Astronomical Observatory speaking with Andrew Dunkley on our sister program, Space Nuts. And this is Space Time. I'm Stuart Gary. A new study claims the Sun will form a visible planetary nebula when it eventually dies. The findings, reported in the journal Nature Astronomy, may help resolve ongoing debate among astronomers about the Sun's ultimate fate. Our Sun will die in about 7 to 10 billion years' time, when it runs out of hydrogen in its core to fuse into helium. Scientists all agree on that. There's no controversy there. Its end days will begin when the Sun leaves the main sequence, expanding into a bloated red giant as it starts fusing helium in its core into carbon and oxygen. During this process, the core will heat up. That's because it's got to be a lot hotter to fuse helium than what was necessary to fuse hydrogen. This increased radiative heat will be enough to force the outer envelope of the Sun to expand, and being further away from the Sun, the surface of the outer envelope will cool, looking more red than the yellow we're used to. As the Sun's gaseous envelope expands, it'll engulf the solar system's inner planets, Mercury and Venus, and probably the Earth and its moon as well. In fact, even if the Earth escapes this fate, our planet's future will already be sealed, ending its existence as a barren, irradiated and superheated lifeless rock without any water or atmosphere. Eventually, the Sun's core will run out of helium, and unlike more massive stars, which can carry on fusing progressively heavier and heavier elements, for our Sun, its life is now over. The core will cool and contract, allowing the bloated outer atmospheric envelope of the Sun to detach, as the white-hot core continues to slowly cool down over the eons as a white dwarf. Now, for 90% of low-mass stars like our Sun, the detached outer envelope will form a spectacular, often very colourful ball of luminous gas and dust known as a planetary nebula. And this is the issue. For years, scientists weren't sure if the Sun would follow the same fate. You see, it was thought to have too low a mass to create a visible planetary nebula. To try and solve this question and finally determine what's going to happen to our Sun, a team of astronomers, including Professor Albert Zylstra from the University of Manchester, developed a new stellar model predicting the life cycle of stars. The new model shows the predicted luminosity or brightness of the ejected envelope for stars of different masses and ages. And that's useful because a stellar envelope can contain as much as half of a star's mass. This expanding planetary nebula can shine brightly for around 10,000 years, heated by the white dwarf at its centre. In fact, some planetary nebulae are so bright they can be seen over extremely large distances, measuring tens of millions of light years, while the progenitor star that formed them in the first place would have been far too dim to ever see. The new model also solves another problem that's been perplexing astronomers for a quarter of a century. See, about 25 years ago, astronomers discovered that if you look at planetary nebulae in other galaxies, the brightest ones always have about the same level of brightness. It was then realised that it was possible to see how far away a galaxy is simply by observing the apparent brightness of its brightest planetary nebula. Now, in theory, this should work for any type of galaxy. But whilst the data suggested this was correct, the scientific models claimed otherwise. That's because old low-mass stars should make much fainter planetary nebulae than younger, more massive ones. And so this has become an ongoing area of debate for more than a quarter of a century. The data clearly says you should be getting bright planetary nebulae from low-mass stars like our Sun, but the models say no. Anything less than about twice the mass of the Sun would result in a planetary nebula far too faint to see. And that's where the new model comes in. It shows that after the ejection of the star's gaseous envelope, the now naked white dwarf at its centre can heat up to 3 times faster than what the older models predicted. And that would make it much easier for low-mass stars like our Sun to form a bright, visible planetary nebula. In fact, the team found that under the new model, the Sun is almost exactly the lowest massive star that still produces a visible, though faint, planetary nebula. And of course that means stars even just a few percent smaller don't. Zylstra says stars with masses less than 1.1 times that of the Sun produce fainter nebula, while stars with more than 3 solar masses should produce brighter planetary nebulae. But for the rest, the predicted brightness is very close to what's been observed. I'm Stuart Gary. You're listening to SpaceTime. China is seeing an influx of private companies trying to cash in on the growing satellite commercial launch market. 2 new companies, iSpace and OneSpace, have each carried out suborbital test flights from opposite ends of the country. OneSpace launched its 9-metre single-stage prototype rocket, Zhongqing Liangguan Star, on a ballistic flight path to an altitude of 273 kilometres. The 2,700-kilogram rocket develops 350 kilonewtons of thrust. The Beijing-based company claims its launch vehicles designed to test technologies which will be used in the company's OS-X series rockets, which it says will be placing 100-kilogram payloads into 800-kilometre-high orbits within a couple of years. Meanwhile, OneSpace is also developing what it says is its new M-series launch vehicle in order to compete for the growing CubeSat launch market as well. The OneSpace flight follows last month's launch of another Chinese startup, iSpace, which flew its new 8.4-metre tall Hyperbola 1S suborbital rocket to an altitude of 108 kilometres. Both operators claim to be using new launch vehicles, which they developed themselves. However, both are very similar in appearance, and the iSpace launch vehicle does look an awful lot like a small retired Chinese military solid-fuel rocket, possibly based on the DF-11 or DF-15 missile. You're listening to SpaceTime. I'm Stuart Gary, and that's the show for now. You can subscribe and download SpaceTime as a free twice-weekly podcast through Apple Podcast iTunes, Stitcher, Bytes.com, Pocket Casts, SoundCloud, YouTube, Audio Boom, from spacetimewithstuartgary.com, or from your favourite podcast download provider. SpaceTime's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C., and available around the world on TuneIn Radio. If you want more SpaceTime, check out our blog where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us on Twitter through @StuartGary, at Spacetime with Stuart Gary on Instagram, and on Facebook, just go to www.facebook.com/Spacetime with Stuart Gary. SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.